Okay, I think we can start. Good morning, everyone. Last week, James and Jeffrey introduced you some concepts about GPU programming with kernels. The idea of today is to see the solution of the exercise that was introduced last week, and keep working with the different memories that we have on the GPUs. Before starting, do you have any questions or anything that you would like to discuss before we start with the solution of the previous exercise? If not, I'll share my screen and talk about the exercise that we will solve now. As James mentioned last week, these exercises take some time, could be a little bit complicated, but we will go step by step, and we will go through the solution. What I will do is, well, I will start, I see that there is a question in the chat if there is a way to measure coalescence with the ROC-M. I would need to check that. Maybe I would need to check that. Because the coalescence is if you access the consecutive positions of memory. So I guess that there might be a metric that could be the cache misses, that this could tell you if the coalescence is okay or not, but I will need to double check that. I'll find the solution and I'll let you know. Cool. So okay, the exercise, I will share my screen. Let's see. Oh, this should work. Okay. So this is the exercise that we will solve today. This exercise we will do this operation, that is this matrix operation, that we have a matrix, and each position of the matrix we'll make this a little bit bigger. We have the entry matrix alpha and two vectors. So we multiply the position I of vector x with the position j of vector y with alpha, and this the result of this multiplication is added to the position of the matrix. For the matrix A, the vector is a 1D, is a one-dimensional on memory, and we will address the positions in that way. I will multiply by the number of columns plus j. this is the way of using a, I don't know if you can see my, here. This is the way of using a matrix that is a 2D as a 1D. We will use a ARCHER2 to see the performance of this operation, and we will see that depending if we use the columns or we use rows, we see that the performance change. So what we will do is, well, first we will start with using a kernel that will be the kernel will be used only with one thread, and from that we will parallelize the while loop, the I loop, and then we will remove this J loop as well, and we will work with the blocks. Also, we will see if the coalescence is right, depending on the performance that we get with the. Okay, so let's start. What I will do is I will I will share the this window. So we are in the further section 203, that is where the exercise is. And if I do ls, I see that they have the template in the exercise in C++. Well, they write me and they submit. So if I, to compile that, what I will do is I will copy the make file that is in the section 2.01. And if we do ls, we see that we have now the make file. So if I type make, it will compile the code, and you see that the exe file is there, is 8 out, and I will submit the sbatch submit. So if I do sq -me, I see that the exercise is already done, and I have I don't know if last time you saw how the results of ARCHER2 they give you I remember that James show you how you can use these results. But now if we see let's learn, there is a way to get rid of all of this, but well, we can ignore this. And we see that the solution is not correct because it's the template, but we will fix that. What I wanted to check is the file. The thing if I refresh this, I'm just checking the file that where we can see the nanoseconds that took the. Moment. Okay, yes, I see here. Okay, it's here. So if it's a cat stats.csv, you see that the number of nanoseconds is 960. Because if we open the file, you will see that here the kernel is empty. So what we will do now is we will populate this kernel. What the SSI said is to use. Let me have a lot of windows open. To use the solution that is on the what is written on the here. I will copy that on the chat. So if we copy that, with copy, no paste. I'm just making the, yeah. If we do that, let's see if the solution now is correct. We need to compile, so with make, submit with this batch submit.sh, and we'll see it is running. Yeah, finish the running. So if we go to yeah, to the last slurm, that is this one. And we see that now the solution is correct. But the thing, this is not parallelized. It's like one thread is doing all the computation. So now we will go step by step. First removing the outer loop, and then removing the J loop. And if we go we print we see that the number of nanoseconds is this time. Actually, we'll make a copy of the number. And we will see how this is done. Okay, so yeah, let's start with the the exercise. So what we want is to remove this loop here. So to remove that, I will well, I can comment this. So it will be something like something like that. Here you see that we're using well, you saw that last week, the dimension of the block multiplied with the ID of the block plus the ID of the thread. And in this case, we will have the thread, the identifier of the. But I will need to check when this is launched. Here. Yeah, it's using 1D. So if it's using 1D, there will be like several blocks. Yeah, this is the core of the. Actually, I think, yeah, rather than I will use this and this should work. Oh, well, let's see if that works or not. Well, one thing that I should check here is if oops. If I is less than the number of rows, in order not to use positions of memory that doesn't exist. I will delete this. Indentation here is not there. So let's try this and see if that works. Yeah, let's see. So this is make. Okay, at least it compiles. Let's execute. Yeah, it's finishing. So I will let's submit. No, I don't want to see that. Let's learn, but I have several ones, so should be the. Okay, it seems that it works because the solution is correct. but we will need to check that the performance. The performance, remember, that was this file here. Let me check if I'm sharing. Yeah, you see that. And you see that now the number of nanoseconds is smaller. I will actually paste here. I will create a file with performance. So you see with the number of nanoseconds, the serial is 128 million, but only parallelizing the while loop, you see that the reduction is the performance is much better, because it lasts only 700,000 nanoseconds. And now the next step is to use to parallelize the J loop. Let me check the and parallelizing that, we will need to use the 2 dimensions. Interesting. So the changes here, I'm not sure if you have any questions, or also, well, this is being recorded, so in case that later this afternoon you want to go again through the solution, you can do so. But well, yeah, the recording will be available sometime this week. So but yeah, please, if you have any questions or anything is not clear, please let me know. Now the next step is the J loop. So for the J loop, is the exercise. You see that we are using threads per block. 1D is 256, but now we will use threads per block 2D, that is 16. So here, when we launch the kernel, the changes that we will do, what I can do is I can comment that, and you will see the difference. And now I will copy and paste here, see if I remember. Yeah. So it's easy. What I will do is threads per block. I will change this to D, and here I will use 1 plus the number of columns that we have, -1 by the threads per block to B. And this is this is like a repeated, I don't know why. Maybe I copied. And here it's important, I need to modify this. Threads per block to B, per block to B. Yeah, it should work. So this is the first change here. Actually, we'll delete that. And the second change here is I will get rid of this loop. So now I need to calculate the index I and the index j. So for the index j, it will be similar to this one, will be block idx y multiply by block dim.y plus thread dx.y. One moment. Well, don't forget the semicolon at the end. And here, oops, sorry. Here I would need to add another condition that a j is less than the number of columns. And let's see if that works. Well, I will just to make this more readable. Also, I can get rid of that. So that will be the 2D solution. Well, if that works, let's see if that. Okay, so the way is make, execute with dispatch, submit. Check, execute minus me. Oops, running. Okay, now it's so let's see if the solution is correct. Okay, it's correct. And check also the performance. It will be, yeah, it will be this number. I will copy the performance. This will be this version. So this will be the solution using the serial is that using a parallelization one loop, you will get this. You will get this performance 700,000, and with the J loop you will get 15,000, or well, close to 16,000, but yeah, way less. What was mentioned last week about the coalescence is the accesses of positions of memory that are one after the other. If we check the code, the size for the coalescence, I remember that it was a figure that what is suggested here is you see that we have I and J in this in this context, but we can try to flip the indices and see if we get a better performance. So what I mean is the proposed solution will be use that rather than the solution that is here. Let's try and see if that we get a better performance. Make but submit. We see SQ me. Oh. We have here this file. Oops, okay, I made that. Yeah, the solution is not correct. I did something wrong. Okay. Is this? Sorry, I mean, this exercise is very tricky, but because I changed that, I think I have to change this as well. Y, X. Make that's init. It's in the queue. Starting and done. This one is the last one. Okay, yeah, I had to flip the. And now let's see if the performance is better or not. So if I cut this one, the performance. Don't know how to call it. Yeah, it's slightly better. Just flipping because when we interchange, we improve the access to the positions of the array are the same that in the in memory. So we get a better performance. I need to check because I think I had a graph that was explaining better that, but I will need to check. So yeah, this is the solution after some time. Yeah, this is what we have. Also the solution, solution is here in case that you want to have a look later. I will share my other screen and it is sharing. We are here. If we go to well, we will see now. Today we will see the manage. Today the idea is study the memory hierarchy of the memory to see what we have on the different memories that we have. That well, we have a shared memory, constant memory, and now we will see manage memory. That this is a way to handle memory, because what we have done so far is a bit manual, but there is a way to do it in using managed memory. But so if we go to this lesson, at the end, or well, in this folder, that the folder is section 204. Here we have the solution of the exercise that we have seen now. Okay, if there are no questions, I will start with the talking about the managed memory. Yeah, I was just thinking. Yeah, I guess this is like a beginning of the. So yeah, the idea is I will explain to you managed memory. There will be an exercise that will be to replace the bits that we have done manually using using a managed memory. That's it. Then we have a break scheduled at 10:30, and we'll be back at 11. Okay, so managed memory. So far, what we have done is explicit memory allocation. So you can see here that we have the host pointer and a device pointer. The host pointer we use malloc for the allocation, and for the device pointer we use heap malloc. If you are using CUDA, will be CUDA malloc. So same with the memcopy. If we're using heap, is a heap memcopy. If we use CUDA, is a CUDA memcopy. So the idea is similar. If here we're using heap, but in case that in the future you want to use CUDA, what you are learning here will apply to the. Okay, so yeah, here we allocate and we copy the memory, and this memory will be in the when we call the kernel, we will send the pointer that is on the device, not the pointer that is on the host. And yeah, good. So yeah, this is like what we have seen so far. This could be I mean, the complicated part here is that you will have two pointers, one of a memory, one that is the host one, the device one. So this will be a bit complex when you have a more difficult structures will not be easy. So a solution is to use managed memory. When you use a managed memory, you don't need a pointer to the memory that is on the host, a pointer to the memory that is on the device. You will have only one pointer. So if you see here the same example, you have a PTR, this pointer, and then you call heap malloc manage, and you specify the number of bytes and the pointer. And here you use the same pointer to initialize let's see, the same memory. The same pointer to initialize the values of the memory. And you see that this you initialize values on host in this part. But when you use the kernel, when you call the launch of the kernel, you use the same pointer. The thing is, behind the scenes here in this point of let's see, of the code or on the execution, the memory will be copied will be copied from the host to the device. But you are not doing this. If we move to the previous example, you do this here explicitly. So you write that line of code. Here is not needed. It's managed behind the scenes. And this, so that this single core heap malloc manage replace malloc and heap malloc. Another point here, performance. At the beginning, maybe if you are not that let's see, familiar with the malloc or have different pointers, a solution could be to use a managed memory. And then once that you have the software that works, you can always move to explicit allocations of the memory and see if the performance is better. According to my little experience, when you use explicit allocations of memory, it is usually faster because you can play or you can do the call to I mean, you manage when you copy the memory from host to device or the number of times that is copied. When you use malloc, when you use managed memory, you need to be more careful. There are ways to tell the runtime, look, copy the memory now or copy the memory later, but yeah, it could be a little bit more tricky. Well, to release the memory is to free the memory is same with the heap free or CUDA free if you are. Yeah, this is what the concept of page migration is that the memory because we have two separate memories, the memory that is on the host and the memory that is on the device. When you copy or when you need the memory that you have allocated on the host, when you need that on the device, there is what is called a page fault. So a copy from host to device will be needed. But yeah, again, because this is managed, this is done by the runtime, and you don't need to bother. Well, yeah, here is explain what I have just said, that allocate the memory on the host space, initialize the memory, and when you call the kernel, the memory is not on the GPU, so it's a page fault. And in that moment, when you call the kernel, is that memory copy that we have done until now, like in previous exercises, will be called. So, for instance, in that case, might be that maybe it's not that efficient, because when you are doing some code here, let me show you. This is the code. So, for instance, between the memory, well, there are ways to do this memory copy asynchronous, and you can do some work here on the while the memory is copying until the kernel is launched. And we have seen, like when the kernel is called, that the memory will be needed, but could be also the other way around. We can execute the once that the kernel finishes and we access the results, the memory will be on the device, will be on the GPU, will not be on the host. So again, will trigger a page fault, and a copy will be done. We can use a prefetching. What is a prefetching? Is when we tell the runtime to do the copy, or because the memory will be needed. You see here that we allocate the memory, we need initialize the data on the host. Here we have the kernel launch, and we know that the memory will be needed on the device. So here we use hitmem prefetch asynchronous, and with that you tell the runtime, look, soon I will need that memory on the device, so please start moving that memory. So it's a hint. You tell the runtime, it's like a heads up that look, I will need the memory on the device. Please start the copy sooner rather than later. Also, we can advise the heap runtime regarding memory access patterns. We have 4 I'm just checking. Yeah, we have like let's say 4 types of advice. If how will be the memory? So data will be only read and occasionally written. So that will help the heap runtime to see if the whole chunk is copied across from host to device, or only a part. Also the preferred location. When you do the malloc manage, when you do the malloc manage, the first time that the memory is allocated could be allocated directly on the device, or could be allocated on the host. Next one is in case that you have different, because you could have different GPUs to different devices, so you can say, look, the GPU, the device 2 or the GPU 2 will be the one that is accessing the memory the most. So, and also for the coarse grain, in case that if you have if you do operations on the matrix that will be like will follow coalescence, good, you have a fine grain, but imagine that you have a sparse matrix or you only check small, random positions of the matrix. You will not need a fine grain of the. That is a good question on the chat regarding the page faults. Is this a crashing error? No, it's something that will slow your program. We have mentioned before, maybe you are familiar about the cache misses that depending on how you access the memory, you could have a more or less cache misses. This will be the performance. The page fault will be handled by the heap runtime. If that is a page fault, means that you want to access a position of memory, and imagine that you're on the device and you want to access a vector, and the runtime realizes that that vector is not on the device memory. So this is a page fault. So they will need to create a copy and move and copy the vector from host to the to device. For performance, we want to reduce the number of page faults, but this is like in general when we use GPUs or even when we use code that is only a CPU. When we use only CPU, what we want to reduce is the page faults or cache misses if we are going to the level of the processor. I hope that makes sense. Yeah, yeah. It's like a page fault is a level of memory of like a RAM. When we are in cache level in memory hierarchy, we call cache misses. So yeah, it's like depending on the level that you are in the memory hierarchy. So yeah, for the hints you have set or unset, you can delete the, let's say, the advice that you have given. On the heap documentation, let's see if that will work. Well, here you will see more. Yeah, more about the. Well, there is always a note that Heapman advice API that yeah, this is like normally, for instance, ARCHER2 the OS is Linux. If you use Windows, it's not still not implemented. At least when this was done, maybe now. And the exercise is the managed memory is to replace malloc, heap malloc, with the heap manage malloc. And rather than having a host pointer and a device pointer, we will have a unique pointer. And yeah, here they said that run the code and also check with the rockprof the performance of this. I think I will. We can solve this exercise tomorrow morning, so you have time this afternoon to play with that. Also, you can play with the prefetched request for the vectors x and y before the kernel and the matrix A after the kernel, and also see if that makes a difference or not. Let's see if. Well, you can also play with that. But yeah, this will be the exercise. I see that we are in like a break time. Do you have any questions or? If not, let's have a break. See you back at 11. At 11, we will see constant memory and the other one, the shared memory. Okay, it's 11, so the idea of this hour is to go through the shared memory and constant memory, and when we finish, yeah, you will have time for questions, exercises. Yeah, we'll be done by noon. Again, any questions, please let me know. I will be more than happy to help. Or if I don't know the answer, I will check that and give it to you tomorrow. Right. So let's continue. So the next lecture is in shared memory. So far, we have used only global memory. Global memory is we have talked about the host memory, host memory, device memory, but yeah, in device memory we have only used global memory. We have also on the GPUs we have a shared memory. And we will learn a little bit more about what's shared memory. This is an example of before introducing shared memory, we will we will introduce a shared memory by an example. What we have done so far to parallelize a function using a GPUs is normally we tackle for loops like this one. We have this for loop, and in the GPU, because we have a lot of threads, we use threads, one thread for each element of this array here. That's why we remove the for loop. So you see that the new version will be this one. In this case, we are updating, let's say, independent locations in memory. The index I is unique, so we read this position on memory, and we update the memory, and we write the update on the same location. So that let's say that there are no conflicts between different positions of memory. The positions of memory are being updated in parallel, and there are no conflicts. It is more tricky when we have when several threads access the same position of memory. We can see this example that we have an array, it's called data, and we want to get all of the elements of that array and add them to a variable, this called sum. So you see in that case that each thread access to a independent position on the array, but updates the same variable that is a sum. What happens? This is what we call a race condition. The problem here is that each thread read the current value of sum from memory and copy that into a register, into like a internal register, do the arithmetic, so do the do the addition, and then store the new result back to global memory. If there are 20 threads using that, it could be the case that you could read an odd value of some, or there could be some conflicts. Could be what is called there non-deterministic behavior. That means will be a race condition. So the problem is every time that you execute the software, you will get a different value, a different result that is not the right thing. How to avoid that? We will need some sort of synchronization. So when we update this variable, the easier way is to do, there is a function that is called atomic addition, atomic add. What it does behind the scenes is that the variable sum has a lock, so get lock that variable, read the value, do the operation that that wants to do, and update the value of sum, and then release that lock. So when one thread is working with that variable, the other threads need to wait, because at the moment that they want to obtain the lock, because the lock belongs to another thread, the thread that wants to access the variable will need to wait. Risk here, or problem here, that you can serialize the, imagine that you have that this is the case for GPUs, you have a lot of threads. One thread accesses the variable and the other threads will need to wait. Then another thread, so because the threads are accessing in a serialized way, or like a one each time, the performance will be similar or worse than when you run the code in serial, not in parallel. So these atomic additions are good, but the idea is to reduce them. You can, when in the exercise, the first solution is just use atomic add. You can check that it's easier because it just changes a line of code, but the performance will be worse than serial, I would say. So we have different atomic functions. We have the, well, addition that could be integer, could be double. And yeah, you see the syntax here. You have the address and the value that you want to add. Well, here, if we click here, you will find more. So we have addition, subtraction, long. You have all of the atomic operations are listed here in the documentation. I see that now, yeah, if the version is 7. Right. Okay, so let's talk about shared memory. Shared memory, well, you need to bear in mind is like is a smaller in size compared to global memory, and is very important that is accessible by all threads within the same block. So each block will have a different shared memory. So that's why when we, if we want to use shared memory, well, you may remember that when if we use global memory, you can use this qualifier, but for shared memory, we use this one, share. That is a double underscore share, double underscore. And you see when you book when you allocate an array here in on the shared memory, normally the array is threads per block, because you will have independent access of the threads that are inside the block, because again the memories the shared memory is accessible by all threads within the same block. And it's faster because it's closer to the CU cores, so you will have well, here this static shared memory, because if you see the array, the size is written here, so it's kind of, yeah, it's called static. You are not doing a malloc here. So the characteristic is speed, because it's faster because it's closer to the compute unit of the GPU. Limited size is not quite big. Normally it's used as a temporary memory to so you may have between the range of 48 to 96 kilobytes. You may find the case that if you use a small matrix or a small vector array, could fit it into the same memory, so you can get better performance. And the scope, I mean, it's convenient when you want to share data between the threads on the same block, or you want to, so that's also benefit. Reduced latency, because it's again, because it's closer to the compute units, will be faster to access that. It's better to share data between the same between the threads of the same block, and also for synchronization. Yeah, you synchronize the threads again from the same. You can do synchronization of the threads of the same block. It's like a way of how to say divide split the memory, or split the computation between blocks, so you will get the benefit of using shared memory that is closer to the compute units, therefore faster, and but yeah, they will need some synchronization that we will see now. And use cases where the third one is a reduction. That the reduction, we will see that at the end of we will see that with the exercise. Matrix multiplication, because you can divide the matrix in small matrices, and you can, if are small enough, you can save that on shared memory, or for stencil computations could be. Yeah, there are different use cases. We were talking about synchronization, and when we use shared memory, it's common. You will see now when you do the exercise that we will need to have a synchronization point at the end of the execution to synchronize the threads that are inside the same block. And the function is this one, sync threads. That is a barrier that normally, again, is at the end of the computation part. Here we have an example that the example is it's called a reverse element. You see that here we have a shared memory. We use the shared memory. That is the size is a threads per block. And we have the index and what we do here. We copy here in temporary we copy so because this is done in parallel, here we will need a synchronization of threads. Otherwise, maybe you get because this array that is in the shared memory is updating parallel. Could be the case that you get access, you read that position of memory, and the thread that was in charge of updating this position in memory of the shared of the array that is in shared memory hasn't done that. So that's why here you need sync threads. If this is like not a clear, when you do the exercise, you will understand better why this is needed when you do some updates in parallel in shared memory. Be careful, and actually this is not only for GPUs, this is like in general, every time that you use, I mean here, okay, we use threads on GPU, but could be the case that you use threads on CPU if you use P threads, or also for, could be, maybe similar to OpenMP. Please don't, when you synchronize threads, all threads will need to access this synchronization point. Otherwise, will be what is called a deadlock, because the threads that meets this condition will reach this synchronization point, but other threads that didn't meet this condition will go, will skip that synchronization point. So some threads will be finished and other threads will be waiting. So please be careful. Never use sync threads inside to avoiding deadlocks is better, not to have a sync threads inside a if or a conditional statement. This is also an interesting concept that we were talking before about. There are some concepts when you work on GPUs. Before we were talking, we were focusing on the memory, and we were talking about, actually last week, about coalescence. And here there is an interesting concept that is branch divergence. That this concept is that the execution on the GPUs is done by wavefronts. Wavefront is a group of threads that execute the same instruction. Actually, are like a unit, are executing parallel, but are executed as a unit. So it is important when you do when you have a condition inside the kernel. Actually, it's a little bit I mean, before that, we were checking that if we were accessing the memory that we were accessing the memory from the vector, or to avoid accessing memory that was not allocated, is okay. It's like actually it's needed. But for divergence or to have like several, yeah, if let's say several paths, if this condition is true, do this, if this condition is false, do that, it will break a little bit the performance. So you should be careful. We were talking that the wavefront is a group of threads that are in the like together. So the threads will be if the wavefront, the size is a 32, the threads will be from 0 to 31, from 32 to 63, and so on. So if you execute different, or if you do different operations for threads 0, 2, 4, etc., inside the same wavefront, you will have a different path, different operations. So that will break performance. The way of avoiding that is taking into account the warp size or the wavefront. I think this is, I don't remember now, in CUDA and heap, the same concept have different names. So I think wavefront is from heap and warp is from CUDA. We need to double check that. But the idea here is the same operation is done by the threads 0, 1, 2, 3, 4 up to 31. So the same the threads that are inside the same wavefront will do the same operation, and threads that are in a different wavefront will do a different operation. Is that clear? So this is kind of a coalescence, let's say, in execution. Well, yeah, in the advice is to reduce the use of conditional statements within kernels where possible, because that break kills performance. Again, here we bear in mind that you don't have that much memory when you use the shared memory. You don't have that much space, so be careful of not yeah, using more, like a break that, or also you can play maybe with the size of the block. So there are ways, but here the main let's say performance concern is that the shared memory is small, so be careful with that. So this is the exercise that I was talking before. So this is to implement this routine d dot, that is a vector scalar product. So we will have the vector x, the vector y, and we will have the result. That result, this one will be the one that will be shared, the variable that we will share, and this is the variable that we will need to be careful and use atomic operations every time that we update that variable. There is a serial kernel here, and the idea is to parallelize that using a heap. The suggested procedure is to use a shared temporary variable to store the contribution from each different thread in a block, and then compute the sum from the block. So what you will do is rather than all threads updating result, only one thread from the block will update the result. So will be like a kind of a update on cascade, let's say, that will be like a two summatories. The first one within a block level, and the last one will be between all the blocks. And in that case, you would reduce the number of logs that you will need to do for the result variable. And well, if you have time, you can also use atomic add, only just use atomic add, and you can see the performance that well, you can have several versions of the kernel and see which one works better. What I will do is okay, we'll wait 3-4 minutes, and 11:30 we will see the constant memory. Actually, this is pretty short, and later I can give you time for the exercises. And tomorrow morning, what we will do is we will solve all of the exercises that we have seen today. Actually, yeah, that's a good question, and yeah, with the thing is with the exercise will be more clear what we want to do with the shared memory. The thing is that we will need atomic additions to avoid the race conditions. But what we want to avoid is imagine that we have like 1,000 threads. What we want to avoid is to do 1,000 atomic additions. Using the shared memory, what we do is we do the update in 2 steps. So the first step is we have a partial sum at the level of the block, and once that we have this partial result, we will use an atomic addition to update the result. And also using shared memory, because it's closer to will be faster. Shared memory normally is used like a temporary memory inside the block. Not sure if that answers your question, but this will be when you do the exercise, or will be clear tomorrow when we see the solution to that exercise. But the idea is that it's like to update, let's say, to get the result in 2 steps rather than directly. And one of the cases is when we use reduction. Okay, so for constant memory, the lesson is shorter. So I will explain what that is, and I can give you like a. Will not be enough time for the exercises, but the idea of this course that in the afternoon you spend some time working with exercises and also checking the lessons in case that you have any questions. Um, yeah. Okay, constant memory. Again, this is we were talking about the global memory that is quite big, but yeah, it's not let's say next to the compute unit, so that will could be slower to access rather than shared memory or the memory that we will see here now, constant memory. Constant memory is when we have, for instance, the size of an array or well, yeah, constant or one parameter that will never change across the execution of our algorithm. So you can store that variable or that value on that small memory. Uh, Again, yeah, the idea also because it's fast and we will see that it may have some like a performance yeah, implications. The characteristics is a read only, so again doesn't change during the execution of the program. Uh, Cache that yeah, the access is faster. On the other way, yeah, the like drawback of what we need to like bear in mind is that it's a limited size. It's like a 64 kilobytes, so we cannot abuse of that memory. Benefits is the performance that we were talking about wavefront. So if one thread of the wavefront read that constant or read that value, the value will be available in other threads. So this will imply a single memory read. We were talking before about like a cache misses, page faults. So mm, this will like avoid all of that. Like one read of one thread will bring the same the value to all threads inside the same wavefront. Uh, Again, the reduced latency because it's closer to the memory is closer to the compute unit will be faster. The latency will be reduced, and you will not need to access the global memory. Well, yeah, is efficient. Use cases, well, the use cases is when you have some everything that is will not change, constant or a vector that that will not change. Yeah, this is like a good candidate if that fits into the constant memory. And well, they said that in theory, when you call a kernel, this everything is a pass by value, and this will like will be constant memory. But also you can explicitly say values that will go to the constant memory. You will need the constant memory space qualifier, and this will be like a vector of 3 elements. I noticed that during this lesson I'm using like a vector array, but yeah, I mean the same concept. So we have this vector or array of these 3 values, and to copy this, to do the copy, we have used memcopy, but here it changed the function name. It's memcopy to symbol. So values is the pointer that is in the host, and data read only is the pointer of the memory that is on the device, that is this one. So you copy from values that is on the host to data read only, that is the memory, that is the constant memory that is on the device. And yeah, this is like if the object is too large, probably the global memory will be used rather than the constant. So we need to be careful. Well, this is like the matrix vector product. That is another. You have the template and you can play with that. And for instance, you can. I don't know what is. Yeah, you can use you can use the constant memory to for alpha, for instance. Also, it's advised that you can use the shared memory to do the product. There are like some you will see that in the repository you have a different the solutions to the exercises. So all of these exercises is just to play and apply the concepts that we have learned today. Well, this is if you have time and you want to complicate a little bit the exercise. Okay, so this is the what I wanted to cover today. We have seen I think I have, if I move here. Also, I would like to, apologize because there is a little bit of, I will try to fix that this afternoon. We have sections here, but here we have lessons. That is a little bit, the thing is that this course normally has been delivered over like 3 solid days. And we got some feedback that 3 solid days there will be like quite a big chunk of time material to digest. So we have split the course into 5 morning lessons. The problem is that some parts could be like lesson 3.1 is actually section 204. So I will need to fix that. yeah, this is what I want. We have seen managed memory, shared memory, and constant memory. And tomorrow we will see more, well, we will see the streams and we see the review of previous exercises. Actually, this lesson was done the previous, but yeah, the second day. So I will fix that this afternoon, hopefully. Any questions regarding today's session? I'll be around until noon. So please, any questions that you may have, let me know. If not, feel free to start working with exercises, or if you need to leave early, please feel free to do so. And also, yeah, thank you for attending today. And in case that, yeah, see you, yeah, tomorrow, same time, 9:30.